On the 27th of December 1984, a team of meteorite hunters from the United States were conducting a search in a region of Antarctica known as Allen Hills. Searching for meteorites in Antarctica is common, and about 2/3 of all meteorites found on Earth came from there. The frozen environment facilitates meteorite visualization. The contrast with the white ice is striking. But on this expedition, a meteorite proved to be unique. Catalogued as ALH 84001, this grayish-green meteorite caught the attention of researchers for its characteristics. However, it would not take them a long time to discover other characteristics that would make ALH 84001 one of the most important and controversial meteorites in history. Its chemical composition left no doubt that it was, in fact, a piece of Mars. But even more than that, its age was extremely high compared to all the other Mars meteorites already found. The ALH 84001 was approximately 4 billion years old. He is still regarded as the oldest meteorite ever discovered from Mars. This age is significant because we possess compelling evidence that Mars formerly possessed liquid water and oceans. And the meteorite is old enough to have formed while liquid water flowed on the Martian surface. But things would get even stranger. Inside the meteorite, several structures resembling microorganisms were found. The structures, which were called microfossils, closely resembled bacteria found here on Earth, both in size and shape. Some had sizes between 100 and 200 nanometers, similar to limits for most common bacteria on Earth, the Pelagibacter ubique. Other structures were much smaller than this, resembling our hypotheses about the first living beings on Earth, made of RNA. The alleged discovery of evidence of extraterrestrial life shocked scientists. The US president at the time, Bill Clinton, even made a TV announcement that you can read here. But today, decades after the meteorite discovery and announcement, the issue remains unresolved. The structures in it could be explained by abiogenic processes, i.e., processes that do not involve living organisms. Still, the structures that appear to be microfossils in the meteorite have helped to drive one of the boldest ideas in science. What if life on Earth didn't start on Earth? Since the beginning of our historical records, humans have been trying to figure out where we come from. For the Greek philosopher Anaxagoras, the seeds of life existed in all parts of the universe. He coined the term panspermia, and it is his earliest known suggestion that life exists ubiquitously in the universe and can be transported and seeded. But a few millennia had to pass before the idea took scientific form. Several scientists had their part in the construction of this idea, but the first suggestion of panspermia as a scientific hypothesis only came in 1903 with Svante Arrhenius, who was also the winner of the Nobel Prize in Chemistry of the same year. According to Arrhenius, microscopic spores could travel through space being pushed by the radiation pressure from our star, the Sun. The problem with this idea is that the efficiency of this solar push decreases as the distance increases, so this mechanism could only work for very small organisms, such as bacterial spores. Another issue, unknown to Arrhenius then, is the impact of radiation on living organisms. It is very difficult to imagine microorganisms surviving hundreds of years of space travel under constant radiation effects. So, for a long time, the idea of panspermia was sidelined in the scientific community. But currently, we have evidence that it can be a valid mechanism for the spread of life in the universe. A lot has changed since the idea of Anaxagoras and Arrhenius. The modern panspermia hypothesis depends on 3 stages, each with its own particularities. The first challenge on the path of panspermia is to be able to remove living organisms from the planet, which in this context is called the donor planet. Nowadays, this may seem easy, especially because we have rockets and robots landing on other planets. So it doesn't seem impossible that accidentally we transport life to another place. This case, in which a civilization, whether accidentally or not, brings life to other celestial bodies, is called directed panspermia. And it is a scenario that will probably be a consequence of our own space exploration if we are not very careful. But what we really want to understand is the validity of panspermia as a means of transporting life, regardless of whether intelligent civilizations exist or not. And for that, we have some evidence. Several experiments conducted in recent years have shown that simple microorganisms such as bacteria can be found at unexpected altitudes, such as above 20 kilometers. Microparticles can be found on the outside of the International Space Station, which orbits Earth at altitude of 400 kilometers. But until today, no microorganism has been detected at this altitude. And this leads us to one of the possible escape mechanisms of the planet that life could unintentionally use: meteorite impacts. This idea is called lithopanspermia, and for now, it is one of the ones we can study better. The concept is that impacts and collisions are an excellent way to move matter between celestial objects. The ALH 84001, for instance, was in Martian soil until around 17 million years ago when a meteorite hit Mars and threw the ALH 84001 into space. It then began a journey of millions of years in space until he stopped on Earth, about 13,000 years ago. And you may wonder, how could anything possibly manage to survive an impact with a meteorite? In fact, most of the material from the meteorite collision and impacted zone is vaporized. But it is in the region around the main collision that the gold hides, or better yet, the chances of life hitching a ride unintentionally. However, we must not forget that microorganisms are sensitive to temperature. And if there is one thing that is quite high during a meteorite collision, it's the temperature. But at present, we are aware that a part of the soil and rocks in the vicinity of the primary impact area can be expelled into space without experiencing excessive heat. And additionally, keeping temperatures that would enable microorganisms to be transported while still alive, protected within these rock sections. No evidence found that for certain they were from living microorganisms inside meteorites. But we have already found several very fragile chemical structures that survived the process of being ejected from the planet into space through a collision. However, this is only the initial stage of a process that relies on numerous factors. What guides us to the subsequent step? Survive the trip. Several studies have been conducted in space to evaluate survival of microorganisms. The first of them, done during the Gemini 9A mission, exposed some fungus spores, such as penicillium, for 3 minutes at an altitude of 150 kilometers. All perished from UV radiation. When shielded from UV using clay or meteorite-like powder, spores of bacteria B. subtilis managed to survive for up to 6 years, defying expectations. The main factor that seems to determine the survival or not of a microorganism in space is ultraviolet radiation. For this reason nowadays, the panspermia theorized by Arrhenius in 1903, in which microorganisms are blown through space by the radiation pressure of the sun, is becoming less likely. But what seems to be the end of one hypothesis is actually the start of another, because now we know that the concept that life can endure inside meteorites is possible, as long as it is protected from radiation. In other words, that's a point for lithopanspermia. The issue is that a meteorite traveling randomly in the solar system can take thousands of years to reach another celestial body. And survival on this time scale is an unknown. Here on Earth, we know of the existence of microorganisms that have survived in a state of suspension inside salt crystals for hundreds of millions of years. Perhaps survival on these timescales within meteorites large enough to shield cosmic radiation is possible. However, even after surviving the trip, we face another problem. A meteorite that reaches enough speed to escape a planet's gravitational pull is essentially a cosmic missile, posing a significant threat. If he goes towards a planet with a relatively thick atmosphere, like Venus, Earth, or even Mars, it is possible that the atmosphere will help in the braking process. Otherwise, if it goes towards one of Jupiter's moons that has no atmosphere, for example, the impact velocity would be too great for anything to survive inside the meteorite. And this brings us to the third, final, and surprisingly most well-studied stage of panspermia, the landing. The final impact is the part that we understand the most currently because we can study it with the more than 50,000 meteorites already found on the surface of our planet. When a meteorite enters the atmosphere of a planet, its surface and the air around it are heated. This is the trail of fire and smoke they leave. But it's important to remember that the process of entering the Earth's atmosphere lasts only a few seconds. What we know is that, depending on the size of the meteorite, its outer parts can function as a type of heat shield, providing shelter for those inside. The ALH 84001, for example, had only 3 millimeters of its surface melted during the re-entry process. In fact, studies and computational models show that it is extremely likely that ALH 84001 has never reached temperatures above 40 degrees Celsius during its existence. Bacterial spores can survive at these temperatures, and this data is incredible in favor of lithopanspermia. In an article published in 2005, spores of the bacterium Bacillus subtilis were placed inside granite blocks. which were then launched by rocket to reach heights of 120 kilometers. And during re-entry into the Earth's atmosphere, the spores that were on the front side of the granite did not survive the high temperatures, but the spores on the side managed to survive. And you may still be wondering, but what about the final impact? Not every meteorite collides with the Earth's surface, creating a crater and a colossal impact. The majority of meteorites are small, and for these sizes, they generally reach the ground with terminal velocity, which is not high enough to form a crater. In summary, if it is possible for organisms to survive the atmospheric entry process, they probably can also survive the final impact with the ground. But, as always in science, caution is an excellent ally. The idea of panspermia has changed a lot over the years, and it is still not widely accepted by the scientific community. On one hand, we are finding more evidence that life may be able to hitch a ride to other celestial bodies. However, to date, we have not found conclusive proof that such an event has occurred in the history of the solar system or on our planet. The main concern here is that possibility does not always correspond to reality in practical terms. Even if it is possible to transport microorganisms from one planet to another, it does not mean that this has happened. Panspermia also doesn't solve the problem of how life originated. It just passes it to another celestial body. In recent decades, an idea similar to panspermia has begun to gather significant amounts of evidence, and it has become known as pseudo-panspermia. But today we know that several organic molecules essential for life can form in space, far from the surface of planets. Some even form before the star itself. We have already found all the nitrogenous bases that form DNA and RNA in meteorite samples billions of years old. And the Earth, during a period that happened 4 billion years ago and became known as the Late Heavy Bombardment, experienced constant impacts from meteorites and comets. In fact, all the inner planets of the solar system have suffered from this, including Mars. Maybe life did not rain on Earth from space, but rather the precursor molecules for life, which when they found a suitable environment on Earth began the evolution. The only certainty we have is that abiogenesis, which is the emergence of life from non-living matter, no longer occurs nowadays, and we don't know why. Several experiments conducted here on Earth have been able to reproduce stages of abiogenesis, but never the creation of life itself. Even if the hypothesis of panspermia is ever proven, the problem of the origin of life will only be shifted to another planet. The question of how life originated will remain open. Still, studying to write this script filled me with a fascination that I hadn't felt in a long time. Imagine the mere and remote possibility that there are meteorites traveling through space today, seeded with microorganisms, just waiting for the time to arrive on another celestial body to begin the long and tortuous process of evolution. It's possible that in the coming decades, with manned missions to other planets, Mars mainly, we'll finally answer the question that keeps many people awake at night. Are we alone in the universe? Or perhaps we have already had company, even on another planet within the solar system? I would really like to know your opinion here in the comments. Thank you very much and see you next time.